Programmable Logic Controllers, PLCs, Introduction. In this presentation, we're going to be looking at what is a PLC and why are they used, the parts of a PLC, the basics of how a PLC operates, and advantages of PLC control. So what is a PLC and why are they used? Well, a PLC is really a computer if you were to take away the screen and the mouse and keyboard. PLCs replace the need for relay logic controls. We can see on the left relays with a number of different timers and dials and things that would then be replaced by a much smaller PLC. The PLC has many advantages over a standard relay operation. Relay control logic requires significant energy, generates heat, and there's moving parts. There's the armature and the contacts, and they fail. It generates a lot of dust from all the contacts that are opening and closing and the arcing that occurs. The seal-in time, as in how long it takes this relay to fully seal in versus this one, will be different. And that difference will be based on the manufacturer, the brand, and the age of the equipment. It's difficult to troubleshoot, and it's difficult to make adjustments in the control sequence. Let's say you need to add another timer into this system. Good grief, what a mess to have to deal with. Not to mention troubleshooting. Ugh, something isn't working properly. Where do you even start? Here's some examples of older relay logic. These are just massive walls full of relays that are connected in specific orientations to provide logical control. Wow, lots of stuff. So a schematic would have been used in, well, olden times, I guess we could say, in order to wire up a relay cabinet. Well, nowadays we are transitioning to PLC ladder logic. And so you would use the schematic to build something similar but not identical in the PLC system. Once the PLC program has been completed in your programming terminal, a laptop or a computer of some sort, you would download it to the PLC. And then you can run the program autonomously without a computer or an internet connection. Computers are assembled with a power supply, a CPU, which contains the operating system, memory, and computer cards that are installed for specific tasks. This here would be a sound card for a gaming computer. PLCs are assembled with much the same items: power supplies, a CPU, which contains the operating system, memory, and PLC cards that are installed for specific tasks. So you can see here the PLC card has a connection on the back and a bunch of circuit chips, but it also has screws on the front for terminations of wires. Now, PLC cards are typically referred to as I/O cards. And these I/O cards are in representing input or output. Now, if they have terminations on the front, they're usually an I/O card. Other cards are not going to have any terminations, and those would be used for different applications. Now, PLCs come in many shapes, sizes, and brands. Small micro PLCs have a maximum number of devices that could be connected to them. They have limited expandability, but can be fairly cheap. You could think of these as the netbook equivalent to a computer. Larger PLCs are assembled. Usually, you would have something like a power supply that provides filtered 24 volts DC to something called the backplane. The backplane, or chassis, is this thing here. It holds all of the PLC cards and provides power and communication between each one of them and the CPU. The CPU is a special card that has the operating system in it and memory, and this connects to the backplane of the chassis and communicates between all of the different cards by using power from the power supply. We can see here this image, a little bit blurry, but the power supply on the far left, a whole bunch of slots. You can see a connection here for each one of the cards. all the way along. This is the chassis. Usually the CPU mounts in the first one here. Yes, I know this is a little bit older Allen Bradley, but honestly, Allen Bradley is kind of the standard in industry, and it's likely you'll encounter these if you do any form of maintenance. Now, PLC cards have wiring connections for different types of field devices, and you can see those on the front. Usually there is a swivel window or door that opens that allows you access to these little screw terminals. Now, PLCs operate by receiving and sending out signals to devices. Signals that are received, so brought back to the PLC, are known as input signals. Signals that are sent out from the PLC are referred to as output signals. So input signals are usually going to be pilot devices or things like push buttons, limit switches, things like that, contacts of a relay. Output signals are usually going to be relegated to very small loads like little lights. That's what this would be, a little pilot light, or maybe the coil of a relay. Now, each PLC I/O card is capable of only one function. The type of function required determines which PLC cards will be used. There are 4 standard types of signals. There are discrete input and discrete output, and there are analog input and analog output. Within these 4 standard categories, there are then a myriad of different voltage values that could be used. Each voltage value would need to have its own specific card. So here's an example of some of the different cards that exist out there. And some cards or manufacturers will have more options available than others. So you can see here for discrete input, there's 1, 2, 3 different types, and you can see the voltage is different for each one. And that voltage is in reference to the voltage that the pilot device would use to bring the signal back to the card. Here's discrete output. There are 3 of them, 120, 48, and 24. Analog input, 0 to 10 or 4 to 20. And analog output, 0 to 10 or 4 to 20 milliamps. We'll talk about these analog values in a different presentation. Now, each PLC I/O card is typically designed for 16 individual signals. And so what that means in a very basic sense is that each card could handle and interpret 16 individual push buttons coming back, and that could be then programmed into the operating system to do a myriad of different operations dependent on a combination of each of these push buttons being pressed. In a typical PLC, you would then have some inputs and some outputs. The inputs would be wired back to input cards. Outputs would be wired back to output cards. So inputs would be things like push buttons and sensors. Outputs would be things like indicator lamps, relay coils, and sometimes contactor coils. Essentially, really small loads. Sometimes an HMI or a human-machine interface is used. This is a screen that displays graphics and data about a control process. These sometimes include interactive capacitive touch buttons for users to access different windows and data. Smaller PLCs sometimes are manufactured with an HMI as part of the total unit, such as this Horner XL. Since PLCs operate without a computer screen typically, having an HMI can be of benefit to provide a graphical representation of the operation if it needs to be shown in a harsh industrial environment. This is the basic layout of a PLC. This PLC has 2 separate cards, an input card and an output card. I have a number of different devices that have been wired to the input card terminals, and I have a number of different tiny little loads that have been wired to the output terminals of this output card. In the middle is the CPU, and this is where the program is contained. Connecting the CPU to the card is a communication bus. We can see it here and here. Notice that there is a source on this side and also a source on this side. They don't necessarily have to be the same voltage. Right now, we can see that the normally closed devices would then be allowing a voltage to be applied to the terminal on this input card, discrete input 1 and discrete input 4. This is a normally open contact, so no voltage would be going to DI3, and that's a normally open push button, so no voltage going to DI2. Now the PLC will read which terminals have voltage. This data is then transmitted to the CPU section from the communication bus. The CPU will then execute the logic of the program based on what data has been read from the inputs. It then decides if any outputs are required to be energized. If so, it will communicate that through the communication bus, and it will then energize by applying its own voltage or a voltage from a source to discrete output 2 in order to energize that load, and then the return path to the source. So the CPU communicates to the output card and indicates which outputs are to be energized. This is referred to as writing in the PLC world. The PLC is unable to take the 120 volt signal from the field devices straight back to the CPU. The CPU is a computer, and the signal required would be extremely small. In addition, any voltage spike in the field wiring could then destroy the CPU. To prevent damage, all PLC I/O cards have some form of an isolating device, sometimes called an opto-isolator. Each individual input and output would then have its own separate opto-isolator inside the I/O cards. An opto-isolator is used to electrically isolate two parts of an electric circuit. The input supplies an LED. The output is a phototransistor. When a signal or current passes through the LED, it shines light onto the phototransistor, which then conducts. Isolation protects the computer from the high voltages and currents seen from the input devices. Here's an example of one type of discrete input PLC card. And be clear, this is not how every single PLC card is manufactured or all of the components inside. But essentially, what you have is an opto-isolator. Then this is the communication bus to the CPU section. This is a Zener diode, which is used to help regulate any voltage that is coming back through this diode. These resistors are in place to try to lower the current value, and this capacitor here is used as a filter. So it's trying to regulate the voltage and the current that is going back into the optical coupler. So this is all inside the PLC input card. When this push button is pressed, current then flows through the optocoupler, applies current, or light, I should say, to the phototransistor, and that is what then communicates to the CPU section that this input has been energized. The digital computer signal is taken to the CPU, and the signal is used in the program. On the other side of that CPU, there may be an output signal, and the output signal is going to be sent to an output PLC card. Again, this is not how every PLC output card will be manufactured, but this one has a diode and another one, so they're inverse diodes to prevent backfeed, and then this is an opto transistor, this is a triac. We have here a capacitor and a resistor, and looks like a metal oxide varistor, which is to reduce the chance of surges, voltage spikes due to energizing of inductive loads. And then we can see here there's a source. So not every output card will look like this. However, you can sort of see some of the basics in its operation. So there is all of the output card components. The CPU section is then going to send a signal out, and that computer signal goes to a little LED, and that light is broadcast onto the opto-isolator, which then sends a signal to the triac, and that's what allows for my system to then energize the light. And so the PLC has allowed for the light to turn on. Now, the basic advantages of a PLC are best shown when contrasted against standard controls. On standard controls, the pilot device controls the flow of load current. The control and the load must be the same voltage or a relay is required. There's one sequence of control available, which in this case, press the button and the light comes on. And finally, load current passes through all the wires. Now let's contrast that against PLC control. In PLC control, the pilot device sends a very small voltage signal to the CPU. So in that way, it's very efficient. There are millions of different control sequences available, not just push the push button down and the light comes on. The control and the load do not need to be the same voltage. This load on the right-hand side might be a 24-volt lamp, whereas the input signal with this push button may only be 5 volts. Finally, load current passes only through the output wires, not through the input wires. So there's a number of advantages and a number of flexible options that allow us to do a myriad of different types of control applications with PLC systems.